So we're going to go ahead and get started. My name is Martin Hyatt. I've been with Powermetrix for about 15 years now. The time does go fast. We're going to go through interpreting CT test results on the PowerMaster today. It's one of the big things we get a lot of questions about when people call in for tech support to raise. They want to know what their CT results actually mean to them. So those are the main things we're going to focus on today. I'm going to go through a couple different slides here for you. I wanted to bring this up. We've got some new people on at Powermetrix, so I wanted everyone to know who is their regional manager for that area. I've got the Western US over there in the green. Kent Lowry is fairly new with us. He'll be handling the middle section of the US. John Jones in red there, he's got some of the Midwest. He's also our director of sales, so he kind of runs the show as far as the sales department goes. And then we've got Jeremiah Swan. He's over on the eastern part of the US. So this is our COVID-19 webinar series. Today, we're going to be interpreting CT test results. Thursday, sign on again, same time. We're going to be going over one of the new products that we have coming out. So we're pretty excited about that. It's a very cool product. I think you'll want to attend that. We do also need more topics, so feel free to request a topic that you would like us to cover. You can email any of us that were just on that last spreadsheet there, and let us know what you want some of these other webinar topics to be about. We do have a product service promo going on, so a lot of people aren't going out and testing right now. So if you've got some downtime, now's the time to get your units in for calibration. Any repairs or any upgrades you may want, we're offering a 25% discount on those through the end of April. So like I said, if you're not going out there with your PowerMasters and using them in these times, feel free to send them in and get a discount on your calibration repairs and upgrades. Moving on. Okay, so let's get into the meat of this here. There's going to be a lot of theory in this. So I hope you guys can stick with me here. It may not be the most fun presentation, but hopefully it's got some good information for you. So what are we going to cover? We're going to cover basic CT accuracy definitions and clarifications of those, okay? And we're going to look at how those clarifications work when you're looking at waveforms, kind of what the math look like, how revenue is affected, numerically. We're going to go over the IEEE parallelograms. Those are the plots that you see on the PowerMasters. We're going to go over some of the user preferences that you can set up within the PowerMaster to hopefully make your life a little bit easier. We're going to talk about what burden has to do with testing. So what do we talk about when we add burden when we do a test? And then we can also measure the burden, okay? And then one of the biggest things is determining if those errors are in a customer's favor or a utility's favor. And we're just talking about the CT errors right now, okay? So those are basically the things we're going to cover. We'll get into the meat of it. Just want to do a quick review of what Powermetrix does and what our equipment does. So we're here to protect your revenue stream, right? So all the products that we use to test CTs have true three-phase reference standards. Those are traceable to NIST. And our products, we try to find all the lost revenue on your site. So we look at wiring verifications, which is what do our vector diagrams look like? What do our waveforms look like? What does our RMS data look like? We can test the meters for you under customer load and phantom load. CT testing, which is where we're going to be focusing today. We're talking about ratio testing, added burden testing, burden measurement, how we can find lost revenue like that. Products also do some other cool things, PT testing, and also what we call an overall test, which is how we test the CT and meter simultaneously. That's a real cool test. So if you ever want a demo or talk more about that, just let us know. But this is what our products do, right? And then what are the actual products? So the newest offering has been the 3 series. This came out a couple years ago. A lot of people have seen this. A lot of you have these. So it's a great little handheld device. Once again, true three-phase reference standard, does all the testing under customer load. And then with this 335 accessory, this is where the 3 series gets into the added burden up to 2 ohms, all right? So there's a resistor network in there with some relays that allow us to add burden onto the CT circuit. And in that, you can also get a 3-phase 5 amp current source for phantom load testing. So that's kind of the 3 series package is really made for transformer rated installations, right? Some of you that have the 7 series and the 5 series, these came out before the 3 series, and these feature much higher current sources. So there's a 20 amp version and a 50 amp version. And these also have voltage sources as well. So if you need a voltage source, this is the product for you. But these are the main products that we're going to be using when we go out and test sites in the field. All right. Also wanted to let everyone know that we've gotten a lot of demand from our customers that maybe can't buy capital equipment, but they want to farm out their testing still, or their meter services, their meter changeouts. So we're actually doing that now. So if you need people to install your meters, to do meter changeouts, if you've got an AMI project going on, if you want meter testing or CT testing done, if you want full site testing plus data analysis, those are all types of things that we can do for you now. So if you have any questions about that, once again, let us know, okay? So let's talk about the actual types of CT tests that we do out there on site, right? So the main one is a ratio test. Okay, that is where we're looking at a snapshot in time of the primary current versus the secondary current and just telling you what that ratio is. So if the CT says it's a 200 to 5, is it really a 200 to 5, right? And you can do that with all of our products that I showed earlier, with the 3 series, with the 5 series, and with the 7 series. And then we also have the added burden testing, where we're actually going to add burden to those CT circuits and then see what happens with the CT. So the 3 series by itself, just the handheld portion, because of it's so small and lightweight, there's no room in there for the extra resistor network. So you can't actually add in burden with the 3 series itself. You can if you get that 335 accessory, and it goes up to an extra 2 ohms of burden that you can add. And then the 5 and the 7 series, they both add up to 4 ohms, okay? And then if you want to actually measure the burden on that CT, that's where the 3 series comes into play. So none of our other products do that, and I don't think any other real products on the market do this, okay? So this is a cool little feature where we're measuring the burden on the CT. We're going to talk about that later in the presentation. Okay, so CT ratio testing. How do we actually look at the signals, right? So we have to connect to our secondary signals. Normally that's done right through the test switch. So these are the duckbill insertion types probes that go into the test switch. If you have CT sites that do not have a test switch, we actually make adapters that go in line with the meter that has its own test switch built into it, or you can even use clamp-ons as well, okay? For primary signals, everyone's seen these. These are the 36-inch Rogowski coils that are the flex CTs. You can use high voltage probes, the SR752 probes, lots of different options there. But the main point is you got to be measuring your primary current and you got to be measuring your secondary current at the same time if you want to do that CT ratio test, right? So for this discussion, I did just kind of choose a CT. So all the screens that we go over, we're going to be saying that we're testing. It's a Durham CT that we had. The ratio
it's supposed to be playing through that microphone.
200 to 5, which is a Billing multiplier of 40, right? Has a rating factor of 2 and an accuracy class of 0.3%, okay? The burden rating on the CT was 0.2 ohms. So all the results that we go over today, this is the CT that we were testing, okay? Now, talking about ratio, everyone's probably seen this CT, what we call the bathtub curve, all right? This is for the ratio error or the amplitude error. So that 0.3% CT, okay, if you look over here on our percentage accuracy on the left, you've got 0.1, 0.2, 0.3%, and then also up here at 0.6%. And then on this axis, we're talking about the percent of rated load, okay? So a normal 0.3% CT only has to be 0.3% accuracy, okay, if it's at 100% of its rated load. Or in our case, for our 200 to 5 CT, meaning we have 200 amps on our primary, up to whatever the rating factor of that CT is. So we had a 200 to 5 CT with a rating factor of 2. So between 200 amps and 400 amps, this CT has to be 0.3% accurate or greater, okay? Now below that, down to 10% of its rated load or down to 20 amps on the primary, it only has to be within 0.6% accuracy, okay? So this is where most people live, right? So very rarely do I see out there in the field where the CTs are fully rated and people are getting the best accuracy out of their CTs. So these are things that we talk about when we say, are we using the right CT for the installation? Are we using rating factors to our advantage? So we want to be down in this area when we're making calculations, not up here, right? So as we get even lighter load, right up in this area, it's really just starting to become noise as a signal, right? So our accuracy really goes off the charts when we get really, really lowly loaded, okay? As we go even higher, the CT goes into saturation. That basically the same thing happens. So this is that bathtub curve. But it's important to know that we're only talking about amplitude here, okay? That's the only thing we're talking about with this plot. So we all know the amplitude accuracy is important, right? It's stamped right there on the nameplate at 0.3%, which is right here. But once again, what about the phase accuracy? Okay, that's what the PowerMaster is showing you as well. So what does the phase accuracy actually mean of the CT? So there's a couple ways to look at this, okay? The first thing we can do is we can just look at a basic waveform, okay? So if you're, and these are, you know, purely sinusoidal waveforms, not real world situations, but what does a theoretically perfect CT look like? So if we had a primary current of 200 amps, okay, we expect our secondary current to be exactly 5 amps, so a 200 amp to 5 amp CT. And also where these peaks meet, right, they're perfectly lined up with each other. So that means we have no phase error in that CT. Now, if our secondary current was down here, kind of where my mouse is there, and it was going opposite of that, that would mean we have a CT wired backwards. So you'd be 180 degrees out, right? But this is what a theoretically perfect CT would look like. Perfectly on the amplitude and the phase as well, okay? So if we had a CT with an amplitude error, meaning it's not putting out the correct amount of secondary current that it should, then you'd see something like this on the waveform. So you've still got your primary current at 200 amps, and then your secondary current is something lower than 5 amps. So right here, it's about 2.5 amps, right? So that's what we call the amplitude error. That's what everyone gets. So when you do a CT test, you say, hey, PowerMaster, I'm testing a 200 to 5 CT, and it comes out and the results are 350 to 5. Well, everyone gets that that's an error, right? That's a billing error that we can all see very easily. But if we look at phase error, so this CT, we've got perfectly 200 amps on primary current. We do have 5 amps on our secondary current, but you see we've got a phase shift here. And this causes billing inaccuracies as well. So there's different ways to look at this. I'm just showing you here what the waveforms kind of look like, right? So when we do a pass-fail with the PowerMaster, we're looking at both amplitude error and phase error that we have. So let's just go into the math just a little bit. And Chris Mullins does say amplitude, the amount of current flowing through the CT. Yes, got it. Okay. So let's talk about what happens when we actually bill a customer, right? So we're going to say this is a perfect scenario. It's a stable resistive load, which is not a normal load, but we're basically saying we don't have any phase difference, okay? So on a CT rated site, you've got watts that are used by the customer, meaning their actual usage, okay? What is that? Well, it's the voltage that they have on the site. We're going to assume there's no PTs. So we're going to just say we've got the voltage on the site times the primary current, that's their actual use, times the cosine of that angle, and that angle is between the voltage and the primary current. That's the customer's actual usage. So if we say if we had 120 volts times 200 amps on the primary current times a cosine of 0 degrees, meaning no current angle between the voltage and the primary, you basically get 24 kilowatts. Okay, that's instantaneous, but we do energy just by time past that, okay? Well, then let's look at what we actually bill the customer, okay? So billing the customer, we have that same voltage times the secondary current, which we're gonna say is a perfect scenario, 5 amps, times the cosine of this angle again, but this time that angle is between the voltage and the secondary current, not the primary current, right? Because that's what the meter is registering. And then times our building multiplier, which would be 40 to 1. So once again, perfect scenario, everything 100% accurate. That's how you bill the customer for 24 kW, okay? The good thing to know is when we're billing the customer, the CT output, okay, that's going to affect both the amplitude that we all get, right? Is it really 5 amps or is it something less than that? And also the phase. So let's dig into this phase here a little bit, right? So this phase angle, once again, was between the voltage and the secondary current now. So that's the angle between the voltage and the primary current plus whatever phase angle error that CT is outputting. So that's how we get this total angle here. So any phase error of that CT output is going to be in this measurement that could cause a billing error, right? So if we look at that on what a vector looks like, sometimes it's easier to look at things in different ways. It makes a little bit more sense. So think of this as like one phase of a 3-phase 4-wire Y, right? So you've got your voltage vector that's at 0 degrees. And then you've got the primary current that, if it's a normal load, will be an inductive load, and it's lagging the voltage, right? So this primary current is lagging the voltage by whatever that degree is, 10, 12 degrees, whatever that is, okay? But that's obviously not what the meter sees. The meter sees the secondary current, okay? So if you have an angle between the primary current and the secondary current because of an error in that CT, it's going to create this billing error here, right? So we're looking at the amplitude of this secondary current and the phase error, okay? That makes up that entire measurement. So sometimes it's a little bit easier to see it as a vector view. Moving forward, so let's look at kind of just a real world scenario saying we've got an inductive load, okay? Just a little numbers for you here. So once again, watts used by the customer, we're looking at the primary signals, right? So let's say we've got still 200 amps, but we've got about a 12% lag between the voltage and current. So now we're down to about 23.47 kW. Now what the meter might see, right? What we bill the customer, instead of 5 amps, you know, our current may be a little low. This is still within spec of a CT. So we're at 4.975. And then maybe we have a 2 degrees phase error that CT is putting out, which isn't a lot. That's just a couple degrees, right? And that math comes out to 23.16 kW. So you're talking 1.5%, something like that. I mean, these things can add up pretty quick. So moral of the story, amplitude and phase of that CT both have to be really good for us to get the best the best accuracy out of our billing, right? That's what it's all about. How do we bill this customer correctly? So now let's get into the fun part. So everyone, when they do a test on the PowerMaster, if you look at your graphs, you'll see what we call the IEEE parallelogram. So this is just another way of showing phase error and amplitude error of a CT. Okay, so there's basically 2 different parallelograms here. Okay, if you look at the inside one, Stephen Schaefer said the fun part. Oh yeah, here comes the fun stuff. So this red parallelogram is for 100% of rated load of that CT. And it's 0.3%, right? So we have plus and minus 0.3% as our limits for the amplitude error or the ratio error, which is on this axis here, up and down, okay? As that amplitude error changes, you are allowed different varyings of phase error on that measurement as well. So for this 0.3% CT, as we get higher in this direction for amplitude error, we are allowed more phase error in this direction. And you'll see that limit here is only 15 minutes, okay? 60 minutes equals 1 degree. So you're talking a quarter of a degree that you're allowed for that IEEE if you're fully loaded on that CT. That's a tight spec, right? Now that same parallelogram just grows a little bit if we're into 10% to 100% rated load limit of that CT, or the 0.6%, right? So as we go up to 0.6% on amplitude, we now get 30 minutes of phase error, okay? So that's half a degree. Still really tight though, okay? But there's two different parallelograms we're looking at depending on how much we're rated on that CT. So let's focus on just the tighter parallelogram, okay? So we're talking 0.3%. Clayton Hullett real quick says, do we have the ability to test high efficiency and extended range CTs? Yes, we do, okay? We're still just gonna measure the primary and the secondary. Just in the PowerMaster, we'll be able to tell it what specs you wanna use as a pass or fail, whether it be 0.15% or 0.3% or 0.6%, okay? So yeah, that's just how we look at the data. How we gain that data doesn't change at all. We're still just measuring the primary current and the secondary current. For this installation, we're talking about, we had the 0.3% rated CT. So this is that parallelogram, right? And once again, this is if we were above 200 amps on our CT, because we had a 200 to 5 CT. So if you did a test point and we measured the amplitude error and the phase error, and we got this little point right here, that would actually fail the CT test, okay? If we got one, and anytime that point is within this parallelogram, we're gonna say that CT passes via these IEEE specs, okay? Moving on real quick, we'll go to the 0.6% parallelogram. So the same theory holds true, right? If you have a point that's inside that parallelogram, it passes via the IEEE spec. If it's outside of that parallelogram anywhere, you get a failure. And that would be if we're between 20 amps and 200 amps on the CT now. So between 10% rated load and 100% rated load. And this is where a lot of people get kind of confused with the CT test results from the PowerMaster, is they'll just look at the data for this point and it might say 200.25 to 5. And this one says 201 to 5. And the one that looks like it's better actually fails. That's because as we had a better amplitude error, we're allowed less phase error, right? So you got to look at both to see whether it passes or fails. Any questions with that? Looking at the text, the chats, everyone looks good. All right, we're moving forward here. So customizing CT error limits, let's talk about real quick. So when we say a CT is 0.3% and 0.6% at down to its 10%, right? What does that actually include? What does that mean? Well, from the CT manufacturer, it's simply the error of the CT itself. That's it. Nothing else. So the physical nature of that CT must be within 0.3% or 0.6% error. Okay. There's no error of the primary or secondary current measurement that's included in that. So I like to say kind of a metal on metal, right? So if we have a CT that's rated 0.3%, and we have a lab type condition where we know exactly the primary current that's going into that CT, and we know exactly the secondary current coming off of it, you should expect to get this 0.3 and 0.6% all day long, right? So one of the questions that we always get from Ray in our tech support is, and this can be an exclamation point or a question mark, why do I keep getting these failure messages on my PowerMaster, right? What is it telling me? Because when we test in the field, right, the CT error that we actually calculate includes all the errors in that measurement, everything, right? So you've got the error of the CT output itself, which has to be within 0.3 or 0.6%. You've got any errors on the secondary current that we measure. Now, this is generally negligible if you're using duckbills because you're metal on metal, right? So at that point, the accuracy of your secondary current measurement is the accuracy of the PowerMaster, which is down to, 0.01, 0.02%. On the primary current measurement, that's what generally causes all the failures, okay? So when we're measuring primary current, we're using things like the flex CTs, the Rogowski coils, or we're using a high voltage current probe. All of these have inherent inaccuracies themselves, okay? That's going to get added into that measurement. You've also got different amplitudes of that primary signal being measured. So if you've got a really, really low loaded CT, not only can the CT not measure that input perfect, but these other probes can't measure it perfect as well, especially if you're really, really low, right? Say you've got a flex CT that's rated up to 3,000 amps and you're trying to measure 5 amps with it on a primary or something stupid like that. So you've also got positioning of the probe. That causes a lot of issues, okay? If you're in a cabinet or a pad mount that's got a lot of VA going through it, you've got loads of magnetic fields that are in that pad as well that are going to interfere with your primary current measurement. So there's a lot more that goes into it than just saying our CT is 0.3 or 0.6%. So what do we do in the PowerMaster then? So you've got user preferences that you can use to your advantage. So this is right on page 1 of our user preferences. You go into utilities, you go into user preferences, and you'll see a spot that says CT test error limits. And you'll see it starts out at 1 times, you get 1.5 times, 2 times, 3 times, and then a user defined, okay? These are multipliers, these are not percentages, okay? So what I generally start people out with is, because you're doing field testing, and you don't want to stand there for a lot of extra time just trying to position a probe perfectly because of the field installation requirements, maybe do a 3 times specification accuracy on your CTs. What that does is it makes that 0.3% CT actually turn into a 0.9% CT. So we get more leeway in those other errors that can cause measurement errors, basically your primary current measurement, right? So this will make your life a heck of a lot easier. So use this to your advantage. Now, if you do that, there's also another page in the user preferences where it allows you to show how you actually display that data. So here you've got an option for IEEE accuracy parallelogram, which would just show you the 0.3 and 0.6%. And then you've also got user-defined accuracy parallelogram. So that's the one I always choose, okay? That way, the way the PowerMaster is calculating it, I'll go back. This is the way the PowerMaster is calculating it, will match how it's displaying it in the graphs, okay? So generally, like I said, do a 3 times multiplier and then make sure you're displaying your user-defined accuracy parallelogram, okay? Moving forward. So what does a PowerMaster actually do when you do a CT test? So the first thing it does is it looks at the specifications of the CT that you chose when you built that site. So you chose a Durham CT that was 0.3%, right? If you don't choose a CT from the site, we assume that that CT is 0.3% by default. So if you leave the CT as none in your site, we're going to assume it's a 0.3% CT, and that's how we're going to do the pass fails, okay? And then what the PowerMaster does is it determines which IEEE parallelogram should be used via the primary current that it measures. So basically, is that CT fully loaded or not? If it is, I'm going to use the tighter parallelogram. If not, I'm going to use the looser one, okay? And then the next thing it does is it expands that parallelogram by that multiplier you chose in the user preferences. And then it ultimately determines a pass fail based on the plotted points within that larger parallelogram. And that's how the PowerMaster actually does its pass-fail calculations. So if you look at it, say once again, we're looking at our 0.3% parallelogram, right? 100% rated load. And we've chosen a 3 times specification. That turns this 0.3% limit into 0.9%. Okay. And also what's going to grow is your phase error limit. So instead of 15 minutes or 1/4 of a degree, we now get up to 45 minutes or 3/4 of a degree. And this is anywhere between 200 amps and 400 amps on our primary. So if you get a point that's still inside the really tight parallelogram, it's obviously going to pass. If you get a point up here that's still within this larger parallelogram, it's going to pass. And once again, anything outside of that parallelogram, the PowerMaster is going to say I'm in a failure mode. Okay. Looking at a couple questions here real quick. Vincent O'Connell says, does this take into account situations where the meter socket is too far away from the CT cable for the probes, i.e. using 2 sets of flex CTs or equivalent for primary and secondary? So yeah, if you have to use probes on both the primary and the secondary current, the calculations and what it does, what the PowerMaster does, is the exact same thing. You're just going to have more possible error introduced into that measurement by the 2 sets of probes. Meaning if that happens, you might even have to take your user-defined multiplier and make it a little bit bigger in that case, just so you're not saying failure all the time, okay? So once again, this is our moving to our larger parallelogram, the 0.6%, 0.6 times 3, you're now up to 1.8%, and you're over to basically 1.5 degrees. And that's anywhere between 20 amps and 200 amps. So those parallelograms just grow, and that's where the PowerMaster does the pass-fail based off of it. This is the first screen that you see when you do a CT test, okay? Where we're going to show you what the measured ratio is, what the nameplate is, either what you chose from the site, right? We're going to show you the primary amps and the secondary amps. Those are your amplitudes. And then we're going to show you the ratio error or the amplitude error and the phase error, both in degrees and in minutes. And then we're going to tell you if the PowerMaster thinks it passes or fails. Now, if you do get a failure mode, whatever fails will show up in red. So for this CT on phase C during this test, the amplitude ratio is okay. We're at 203.03 to 5, but our phase was 180 degrees out, meaning the CT was wired backwards, and that's why it shows up in red. That's what caused that failure mode, okay? Moving forward. This is the biggest question that we get sometimes, right? Everyone's familiar with if a meter is fast or slow or not, and whether that is in the utility's favor or whether that is in the customer's favor. Not so cut and dry when you're dealing with CTs, okay? So if we look at, once again, we're looking at parallelograms here. I know it's fun stuff, okay? If we look at this axis over here, right? Remember, this is our amplitude error. So at 0 error, our CT would be at 200 to 5, okay? As that number gets higher, meaning 201 to 5, 202 to 5, 205 to 5, that's in favor of the customer, right? Meaning the CT is actually putting out less current than it should. So as that ratio gets higher, that's in favor of the customer. As it gets lower, so 199 to 5, 198 to 5, 170 to 5, that's in favor of the utility. And those never change. Up, favor customer, lower, favor of the utility. Now we have to talk about the phase, right? So our phase error, once again, is on this bottom axis here, going left to right, the x-axis. As we move to the right, okay, that is more of a leading phase angle, and that's secondary current with respect to primary current. As we go left, you can say it's lagging the primary current, okay? So if you look at up here in this quadrant where we kind of normally are, right? We're moving this direction with the ratio, and that is in the customer's favor for amplitude, right? As that happens, we're allowed more leading power factor between primary and secondary current, and that's actually in the utility's favor, okay? So that's why they came up with this parallelogram, right? That's the main theory behind it. As we go higher in the customer's favor, we're allowed more in the utility's favor on phase to kind of balance things out. Now, it's important to recognize that this is for inductive loads, okay? So if you think about it, on our vector diagram, our primary current is going to be lagging our voltage, okay? And then we're putting more lead going this way, which is going to help kind of even that out, okay? So that's how that works. So up in this quadrant, if you have an inductive load, you have in favor of the customer on the amplitude and the utility on the phase. If we come down here, you're in favor of the utility on the amplitude and the utility on the phase. So if you get lots of results down here, you're going to have some customers that are ticked off at you. And then it just kind of goes around, right? If you come down in this quadrant, you've got in favor of the utility on the amplitude and the customer on the phase, okay? So is the CT fast or slow? This is a good slide to keep looking at, once I said, for inductive loads. Okay, moving forward. How you can see that on these screens as well, okay? So once again, positive numbers on the ratio error favor the customer. So ratio error is positive. That favors the customer. Phase A there, phase A here, see we're in this top right-hand quadrant. And then positive numbers on the phase error favor the utility. So once again, positive on our phase error, we're moving this direction, right? And that's where you kind of want to live, right? But that's how you see that on the very first page here. Moving forward, going into our second type of test, now we're talking about added burden, right? What we can do with that type of test. And you can do that with the 3 series, as long as you have the 335 accessory, and then with the 5 series and 7 series. So when you're looking at doing a CT test, we've got 2 basic types of tests we do with burden, okay? You've got burden and ratio, and then you've got burden only test. So if we do a burden and ratio test, we're basically going to perform that same ratio test, what I like to call the installed burden, or whatever burden is currently on that site. And then we're going to do ratio tests at different added burden steps. So then we're going to do a ratio test after we add 0.1 ohms of burden. And then we're going to do a ratio test after we add 0.3 ohms, then 0.5 ohms, then 1, all the way up to 4 ohms, okay? A burden only test, maybe if we left our primary probes at home, or I can't get to the primaries, right? Then I can only look at the secondary current. So what we can do there is we can measure the secondary current's amplitude and then see how that current changes as we add extra burden, 0.1, 0.3, 0.5, 1, 2 ohms, etc. Those are the 2 main types of tests we do when we're doing burden. Now, the results page looks exactly the same if we're doing a CT burden ratio test, right? So nothing on here says anything about burden. If you want to see what actually happens, you need to press F4 and go into your graphs, and that's where you can see all the results. So now what you'll see when we look at your parallelogram, right? This is our user-defined parallelogram. you've got pass fail based upon just the installed burden test point. So this very first test point here, right? Okay. So that's the error as the CT installation currently exists. And then these other points are as we add burden to that circuit. How does that amplitude of that CT change? How does the phase of that CT change? And you can see a lot as far as how much headway you have if something ever were to happen with the burden on that site, okay? Over here, it lists how your ratio error changes, and then also how your secondary current changes as you add extra burden as well. But if you want to see all that data, you have to go to the graphs, okay? Moving forward, for CT burden only testing, this is what the graph looks like. So you're not seeing the parallelogram because you're not looking at any ratio between the primary and secondary, because we're just looking at the secondary current. And this basically just shows us how our secondary current is changing as we're adding extra burden to that CT. What you don't want to see here are sudden sharp changes in the secondary current. Like if it goes to 0.1 ohms and then drops off the charts, that's saying, well, now I'm definitely in an overburden situation as we stress that CT, right? Moving forward, our last type of CT test is the burden measurement, okay? And this is something that the 3 series does that I don't know of anything else in the industry that actually does that. It's a really, really cool test. And what it does is we're actually measuring the burden on the CT, okay? So how do we prove that a CT is operating within its maximum burden rating? It's just Ohm's law. It's just voltage equals current times the resistance, okay? What we're searching for is what this resistance is here. So we're doing that by measuring the secondary current with your duckbill probes or clamp-on current probes like we normally would. And then what we need to do is we need to measure the voltage drop across the secondary of the CT. So instead of having our voltage clips on secondary voltage up here, 120, 240 volts, we're going to move those down to the terminals right on the CT. And we're going to measure that voltage drop. So if we have the voltage drop across the CT, we know the secondary current, we can calculate this resistance or the ohms of burden on that CT. So can we prove why this CT ratio test failed? So this is just a 3 series test. We did a ratio test, right? Single point. Phase A passes great, phase B passes great, phase C fails at about 3% on ratio error. So it's kind of an outlier up here, right? So the question is, can we actually prove why this happened? Well, what I would do, number one, make sure that your CT probes, your primary probes, are positioned well. Maybe change them a few times to see if this is a true error or not. If it is, save this result screen, right? And then what we want to do is we want to actually measure the burden and see if that CT is overburdened or not. So when we do that, we can prove that phase C had way more burden on it than phase A or B. So you look here on phase C, we had a failure mode on our CT burden test, and it's because we had a lot of voltage here across the secondary of that CT. Okay, 3.87 volts compared to 60 millivolts on phase A and B. Okay, so we've proven that that CT failed because it was overburdened. Hopefully it's just a loose connection. If it is, save this screen, right? Tighten everything up, and then go back and do your CT ratio test again and watch it pass. That way you can show Mr. Customer that here was the results before the test. Here's why it failed. Here's the results after I fixed it. This is the reason that your bill is going to be going up a little bit, right? So always save those results. Just a little thing I want to say here. Even if all my CT results pass, meaning on that first screen, I always, and I mean always, look at the graphs as well to see if I have any possible problems that could come up, right? So this is that same result we looked at before. And you'll see on phase C, it passed, but it's a little bit further out than these other ones, okay? The question is, if something were to happen in the future, is there a decent chance that this could end up costing me lost revenue? Well, the CT is close to failing, okay, as we add 0.1 ohms of burden on this test point right here. Now, what we don't know is the true burden of that, right? The true burden of that test point is whatever the installed burden was, plus the 0.1 ohms that we added to it. So until we know this amount of burden, we don't know what the total burden rate is here, right? So let's look at a couple scenarios. So let's say our CT is rated at 0.2 ohms. We got something like this, and we had a few extra minutes, and we want to kind of dig into this, this scenario here. So let's measure the burden at this test point with our PowerMaster 3 series. The measured burden, we'll say, was 0.02 ohms. That makes the total burden 0.12 ohms at this test point, okay? Which is well beneath the 0.2 ohms that CT is rated. If I saw that, there might actually be a problem with that CT, because it shouldn't be that close to failure at that burden. That burden is well beneath what the CT is rated at. You should get better results than this, okay? So with that one, there might be a problem with the CT, that if you get any extra added burden, a little bit of a loose connection, a little bit of a degraded wire, you're going to start losing revenue on this worse and worse, okay? Let's look at the same thing, okay? But this time, when we measured the burden, we'll say when we measured the burden, it was maybe 0.34 ohms. That would make that total burden at this test point 0.44 ohms, okay? And we'll say the other phases had much lower burden. This might be a problem with the wiring. The CT is fine, right? You might have a loose connection somewhere that's causing this high burden, but the CT itself is actually doing great. So it's still within spec, even at more than double of its burden rating. So the problem here, not the CT, it's more in how that you might have a loose connection or something somewhere, right? And let's look at another one I've got here. So let's say this time we measured the burden was 0.22 ohms. That's going to make the total burden 0.32. And we'll say all the other phases measured at about the same thing, right? What you might say here is this CT might have been improperly spec'd, okay? You might have a long distance between the meter and the CTs, okay? So the CT is actually working decently, right? It's over its burden rating by 0.12 ohms. So really, when this site was installed, you probably should have had just a higher ohm rating CT. So once again, this might be something when you dig into it that might have just been the wrong CT that was put in there, okay? So lots of different things that you can diagnose by being able to measure the burden on that CT after or before you do a burden and ratio test. So there's lots of data that you can get there, okay? That is the end of my presentation. I know there was a lot of theory. I hope I got through it in an hour. We're 8 minutes short, so we did a pretty decent job. Are there any questions that any of us have right now? I see Chris has been talking with some people on the chat. Okay. Looks like some questions about how much burden you should add. Generally, if I'm out on site and I see a burden on a CT that may be rated at 0.5 ohms, I generally have people put the max burden that they add as either 0.5 or 1 ohm. Just enough so that you know you're going to send that CT into a situation that is above its burden rating, just to see how it performs if something bad were to happen. And that's kind of what I do. If no one has any more questions, I think we'll go ahead and sign off. Thank you everyone for attending. I know it was lots of theory, Everyone, please stay safe out there. Prayers to everybody. And that's all I've got. So I will sign off. You guys can stay on the chat with Chris Mullins to get the addresses and anything like that.